Yeah, let's start looking at this concept of regression. One of the things typically heavily used as a part of predictive analysis. Whenever I want to predict something based on something else, let's say I want to predict the stock price based on the the uh, the performance of the company, based on the profits of the company, based on the sales of the company. Let's say I want to predict some value based on one or more other variables. We are using the concept of regression, right? So probably if I just on a simple terms, let me take one data set irrespective of any background. Let's say I'm collecting the details about some patients, wherein the most important thing, let's say I'm collecting his weight, I'm collecting their cholesterol levels, I'm collecting their blood pressure, blah 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 blah. Now I want to see whether the cholesterol is dependent on weight and blood pressure, right? I want to see whether I can predict based on the weight and the blood pressure levels, or probably age, any of the factors. See, basically I am trying to build a relationship between one or more variables, so that by knowing one of them I should be able to predict the other, right? Probably as simple as I know the based on the GDP of the country, can I predict the sales of my company? So if one value is known or based on some characteristics of the product, can I predict the price of that product? Let's say a TV, there are so many TVs that are available with so many technical specifications, and these are the prices. Now can I build a relationship between the price and all these characteristics, right? If I can build it, the advantage is, if tomorrow I have to predict the price of a new television that is coming into the market, I can use that model. That is what is being achieved by your regression in a statistical parlance. So basically I am trying to predict something. So basically in this I'll make a very crude example to you. I want to predict the cholesterol levels of the person based on weight and the blood pressure. So let's say I have some 100 people's data with me. Using this 100 people data, I want to create some kind of a equation. Cholesterol equal to something times weight plus something times the blood pressure. Here this is not a scientific formula, right? No scientific relation, but just based on the observation of the data, we are building a relation. So that kind of a relationship building between this is called as the dependent variable. I'm making this dependent on the other two or other three. So this is called as a dependent variable, and whatever are the variables, blood pressure, weight, age, if at all I am considering these things, I am calling them as independent variables. So in any regression, first thing we have to talk about is a dependent variable. There will be one dependent variable, but there can be more independent variables. And from our standpoint, if there is one independent variable only, we call it as one regressor or simple regression. If I take only one, but if I take more than one independent variables, we call it as multiple regression. No big difference between the two. If I take only one variable as independent, so probably if I want to build a relationship in this example, saying, okay, cholesterol is dependent only on weight, then the model which I am building is called as a simple regression model. If I say no, cholesterol is dependent on age, weight and blood pressure, more than one, then we are calling it as multiple regression. So if we consider a multiple regression model, simple regression is automatically included in that. Instead of 3, we are taking 1, And that is what is a simple regression for us. Now, how do we typically do that kind of a regression? Right? So in this case, just for the terms purpose, this cholesterol is my dependent variable, and blood pressure, weight, and age. These three I'll take for time being. They are my independent variables. And one more thing is the dependent variable should be a continuous variable. Should be a number. Quantitative variable. It cannot be a qualitative variable. Right? I can't predict gender, or I can't. I mean, there are different ways of predicting them. But as far as this regression as a tool is concerned, our dependent variable should be a number kind of a variable. Independent variables, they can be numbers, they can be quantities also. They can be qualitative, like gender also can be there as a part of the independent variable. How we handle that, I'll tell you. There is a concept called dummy variables. So we will come to that aspect. But for time being, even our independent variables, I am taking them as age, weight, and blood pressure, which all three are number based variables itself. Right? Now, how does this regression equation work out? The simple thing in this regression equation is it it writes the equation like this now. Right? Any regression equation, it gets written as now cholesterol equal to some A times the age. So A has to be determined. What is this A? We have to find out. Plus B times let's say weight, plus C times something else, blood pressure. This is the equation for me. Right? So, because we are building it from the data, A, B and C cannot fit in exactly for all the values. Right? Because see, if it is a scientific relation, I may say cholesterol equal to 2 times age plus 3 times weight plus 1.5 times blood pressure, something. But that is not a scientific relation which should be universal for everyone, right? We are using our sample data and based on that trying to build the best possible relation. We are not saying it's a scientific relation. Out of the data that is available, what is the best value of A, best value of B and best value of C? So that best is not the best, is not 100%. Right? So probably it's like this. Now when I plot a graph for all these, let's say I am getting more plots like this. If I ask you to draw one single straight line which will connect all the points, it's not possible. It cannot connect all the points. But what we can do is we'll draw something which is a best fitting. When we define a best fitting, it is nothing but the errors are as minimal as possible. The errors are as minimal as possible. So determine the equation of your line based on the fundamental that your errors are as minimum as possible. That is what a regression typically does. So when we are using a regression from a prediction standpoint, it gives an error also for each value. For each value there is an error, but the minimized that error is, that is the best fitting equation for us. Now let me try running this regression and we'll try to interpret one by one. Right? So here when I use this spreadsheet kind of stuff to run this regression, let me run the regression once and we'll discuss each and every point. So in the regression, so we'll do the calculations part first and then the understanding theory becomes more easier here. So in the regression, I want to predict, probably here, let me just make some modifications from a spreadsheet perspective. Okay, for time being, let me just take these two. Okay. All right. So I am taking, let's say, cholesterol as my dependent variable, and I'm taking, let's say, a combination of weight and blood pressure. Two variables I'll take for now. So I'll add the third one slightly later, and I'll show something more there. I'm taking two variables. So because I'm taking two variables as independent variables, we call it as multiple regression. If I take one, it's a simple regression. And let's see what output it gives to me. Let me see what output that it gives to me. Okay, it is giving some kind of this output. So if we are able to analyze this output better, the whole regression is understood fully. If this output you can interpret it, the whole concept of regression is easily understood. Now, the first thing we are starting off is with the coefficients here. What are the coefficients that have come out? As I said, the equation cholesterol equal to A times the age plus B times the weight, something like that, plus some constant also will be there, plus some constant D. Right? Now, this constant D, technically we call it as intercept. Right? This constant which has no relevance to any of the variable, whatever the constant that comes up, we call that as intercept. So in our example, we got the intercept as 134. So it's like probably in our equation, it would be like plus 134.00 plus D, AX plus BY plus CZ plus D. And we are also saying the coefficient of weight is 0.1472. So it's as good as saying 0.1472 times the weight. In the equation, cholesterol equal to 0.1472 times the weight plus 0.544 times the blood pressure plus this. This is what is our equation. To start with, if I have to talk about what is the relationship equation between cholesterol and the other two parameters which we have considered, it comes out saying the equation is 0.1472 times the weight plus 0.544 times the blood pressure plus 134.02. So this is called as intercept, and these are called as the slope coefficients. These are called as the slope coefficients. And in case of multiple regression, we call them as partial slope coefficient, because there are multiple variables. Each variable we call it as a partial slope coefficient. Then how do I interpret these? The interpretation is very simple. When weight is 0 and blood pressure is 0, a person having a 0 weight and a 0 blood pressure will have a cholesterol level of 134. Because the equation is what? AX plus BY, right? This into weight plus this into blood pressure plus 134. If weight is 0, blood pressure equal to 0, cholesterol equal to 134. So the simple way to interpret is, for a person with a 0 weight and this may not be an apt example in this case, but just try to correlate with the concept. So for a person whose weight is 0 and a blood pressure equal to 0, the cholesterol levels are equal to 134. That is what is the meaning of intercept. Then, how do I interpret these two coefficients? For weight, 0.14 times the weight. So for every 1 kg increase in the weight, for every 1 kg increase in the weight, keeping the blood pressure constant, the cholesterol will increase by 0.14 units. So if the person's weight increases by 1 unit and the cholesterol and the blood pressure does not change, his cholesterol level will increase by 0.14 units. And the same logic I can apply to the blood pressure. If the person's blood pressure increases by 1 unit without anything else changing, his overall cholesterol levels will increase by 0.54 units. So basically, just by looking at these numbers, we are able to build up the relationship between the dependent variable and the independent variables. Now, the real problem starts in terms of how good is this relation. It has built some numbers, right? It has built some numbers. Now what I want to drive is, assuming that these are some numbers, I want to use these numbers for predicting my cholesterol for all the 100 people. I know the weights of all the 100 people. I know the blood pressure levels of all the 100 people. So using this formula, I want to predict the cholesterol levels for them. I can do that. Now let's see how good are that numbers. So probably let me call this as predicted cholesterol. So what is that I will do? I will take it as the this much times the weight. What is the weight of this person? This is the weight of the person plus this much 0.54 times the blood pressure of the person plus probably the intercept. So as per this model, the predicted cholesterol for this person should be 210.58. But what is the actual? 193. So the predicted, that is the error. Predicted and the actuals, whatever is coming out, that is what we are calling as the error here. Alright. Now let me do the same thing. For some people it may be very high also. You see here, for this person, probably for this person, it is matching extraordinarily. 206, 206. So in some cases the matching is happening. In some cases the matching is very bad also. You see here, 164 is actual, whereas your system is predicting 227 for this person. So now, how do I identify